Welcome to Lecture 8. This week we start Chapter 5. We'll talk about area and estimating with finite sums, sigma notation and limits of finite sums, and then we'll talk about the definite integral. First, let us discuss area and estimating with finite sums. But I'm just going to give a quick recap of this section. A lot of the things in this section I think are not relevant, so we'll just go through this quite quickly. You can read more details in the textbook if you want to. Because I'm going through this section very quickly, that means that today's lesson is going to be a shorter than normal lesson. We don't need very many slides to cover everything that's on the syllabus for this week. I start with the question, look at this graph, look at this area underneath this graph between the x-axis and the y-axis. I'm calling this region R. And the question is, what is the area of R? Well, we can approximate R using two rectangles like this. I'm using rectangles so that the rectangles are bigger than the area that they are approximating. So this is called an upper sum. Upper sum means the rectangles are bigger than the area. It's easy to calculate the area of two rectangles. As you can see at the bottom, first rectangle has width at a half and height 1, so 1 multiplied by a half. And then for the second rectangle, the width is also a half, but now the height is 3/4. How do we know that the height is 3/4? Because the top left-hand corner of the rectangle is on the graph. If we put a half into the formula 1 minus x squared, we get 1 minus a quarter, that's 3/4. So just by calculating the area of these two rectangles and then adding them together, we can estimate that the area of R is approximately 0.875. That's not a very good approximation because we can see from the picture we have a lot that's area that's in the rectangles but it's not in R. If instead of using two rectangles we use 4 rectangles, then we can get a bit closer. Again, we can calculate the area of these. Now the width of each of these rectangles is a quarter, and by calculating the value of the function on the left side of each rectangle, putting the left x into 1 minus x squared, we can calculate the height of each rectangle. And I'll leave it for you to check that the area of these 4 rectangles is 0.78125. That's still bigger than the real area of R, because we have a little bit of area which is outside. We can do better if we increase the number of rectangles. Let's suppose we did 8 rectangles, or 16 rectangles, or 32 rectangles, etc. As we increase the number of rectangles we're using, the area of the rectangles in total is going to get closer and closer to the real area of R. So that's upper sum, but there's another way we could do this. We could use a lower sum. We could choose our rectangles so that the rectangles are always inside the region R. There's 2 rectangles here. The first rectangle has width for half and height 3/4. 3/4 because now the right-hand edge is on the graph. And there's actually another rectangle down here. You can't see it, but its height is 0. We can add up the area of these 2 rectangles. The area of the left rectangle, of course, is 3/4 multiplied by a half. And the area of this rectangle of height 0 is 0 multiplied by a half. So our first lower sum approximation is 0.375. And as before, we can improve this by increasing the number of rectangles. 4 rectangles, 8 rectangles, 16 rectangles, 32 rectangles, etc. Always choosing the rectangles so that they fit inside the region R. And there's a third approximation we could do. Upper sum was choosing rectangles which were outside or including R. Lower sum means choosing the rectangles inside R. And because we have a decreasing function for a upper sum, we were using the left-hand edge of the rectangle to decide its height. For a lower sum, we're using the right-hand edge. Just because it's a decreasing function, we're using the right-hand edge of the rectangle to decide its height. Let's suppose we use the middle of the rectangle to decide its height. So at the point a quarter, we can go up, calculate 1 minus a quarter squared, and that will give us the height of this rectangle. Or we could do the same thing with 4 rectangles, say. All of these rectangles have a width a quarter, and the heights I'll leave for you to double check are 63 over 64, 55 over 64, etc. When we add these together, we get our approximation 0.671875. And it's still not exactly right, but it's not too bad, because every time we have a bit of area which is outside R, we also have a bit of area inside R which we've not counted. So these roughly cancel out. Again, we could increase the number of rectangles to improve our estimate. Once we get to, say, 32 rectangles, then we're going to be quite close to the area of R. The number I've taken from your textbook for lower sum, midpoint sum, and upper sum. As we increase the number of rectangles, 2, 4, 16, etc., this table gives the values of the lower sum, the midpoint sum, and the upper sum. So, for example, if we're using 1,000 rectangles, then it looks like we're getting quite close to 0.6 recurring. Now, the idea here is that as n increasing, as the number of rectangles increases, the estimates are going to get closer and closer to the real area of R. What we want to do is we want to take the limit as n tends to infinity, but we can't do that yet because we don't have enough notation. That's all I want to say from section 5.1. I want to very quickly move on to section 5.2 and start talking about this signal notation that we're going to need if we want to take limits of finite sums. If we have some numbers added together, if our numbers are A1, A2, A3, up to say AN, and we want to add them all together, we could write this as I could write A1 plus A2 plus A3 plus A4, etc., etc. But there's a neater way to write a sum like this using the capital letter sigma. This symbol is the Greek letter capital sigma. The k equal to 1 on the bottom tells us that we're going to start our sum when k is equal to 1, and the n on the top tells us we're going to finish adding these terms together when we get to n. And then we have ak, which is going to be the formula for the kth term. So, for example, if I wanted a neat way to write 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared plus 9 squared plus 10 squared plus 11 squared, we can use sigma notation. Capital sigma, the formula for each one of these numbers is k squared. The first one is when k is equal to 1, and the last one is when k is equal to 11. So this is the sum from k is equal to 1 to 11 of k squared. Or in my next example, I have 100 numbers added together. F of 1 plus f of 2 plus f of 3 plus dot 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 plus f of 99 plus f of 100. I can write this as the sum of f of k from k equal to 1 to k is equal to 100. Or going the other way, if I see the sum from k is equal to 1 to 5 of k, then I know that that means 1 plus 2 plus 3 plus 4 plus 5. Start at 1, finish at 5. Add these up, we get the number 15. Some more examples. The sum from k is equal to 1 to 3 of minus 1 to the power k multiplied by k. So what do we have? We start with k is equal to 1. So that's minus 1 multiplied by 1. And then we put in k is equal to 2. So minus 1 to the power 2 multiplied by 2. And then we do the same thing, but with k equal to 3. So minus 1 to the power 3 multiplied by 3. And I'll leave it for you to check that that is all equal to minus 2. Another example, the sum from k is equal to 1 to 2. So we're starting at 1 and we're finishing at 2. And the formula is k over k plus 1. So 1 over 1 plus 1 plus 2 over 2 plus 1. And that's 7 over 6. The first 5 examples I've given have all started with k is equal to 1, but we don't have to start at 1. We can start anywhere we want. Let's suppose we want to start with k equal to 4, and we're going to finish with k equal to 5. If our formula is k squared over k minus 1, first we do 4, so 4 squared over 4 minus 1. Then we increase to 5, 5 squared over 5 minus 1, and then we stop. And I'll leave it for you to check that that's 139 over 12. If we have finite sums, we can add them together, we can take the difference, we can multiply them by a constant in all of the ways we expect. For example, the sum of AK plus BK is the same as the sum of AK plus the sum of BK. Or if we have a number C, we can take that outside of the sum. The sum of CAK is C multiplied by the sum of AK. The fourth rule is if we're adding a number. If we have C plus C plus C plus C plus C plus C, we just have n lots of C, so just n multiplied by C. Some simple examples. The sum from k is equal to 1 to n of 3k minus k squared. I have a formula, 3k, minus a formula k squared. So I can split this up into two sums. I can also take the number 3 outside of the first sum. So 3 sum of k minus sum of k squared. I can take a minus sign outside because minus just means minus 1 multiplied it. So we just get a minus in front. Example C is an example where we have a sum of 4. So we have 4 plus 4 plus 4. 4 plus 4 plus 4 is 12. 3 times 4 is 12. And then finally, in D, we're doing the sum from k is equal to 1 to n of 1 over n. But there's no k here. 1 over n is just a constant compared to k. And a constant we can take outside. So really we have 1 over n multiplied by the sum of 1, or 1 plus 1 plus 1 plus 1 plus 1, or which is just n. So really here we have n multiplied by 1 over n, or 1. Now, something we're going to need later, I want to find a formula for 1 plus 2 plus 3 plus 4 plus 5 plus dot 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 plus n for the first n, for the sum of the first n natural numbers. And instead, I'm actually going to find a formula for double the number I really want. Instead of looking for 1 plus 2 plus 3 plus etc., what I'm going to do is I'm going to first find a formula for 2 times this. And then after I find this number, I can divide it by 2 and I can get the formula that I really want. Now, 2 times 1 plus 2 plus 3 plus 4 plus 5, we have one lot of this sum. And then we have another lot of the sum. So we could do 1 plus 2 plus 3 plus 4 plus 5 plus ... plus n plus, and then the same thing again, 1 plus 2 plus 3 plus 4 plus 5 plus ... plus n. And we could change the order around however we want to. The first one, 1 plus 2 plus 3 plus 4 plus 5, etc., I'm going to leave as it is. But the second one, I'm going to change the order of it. I'm going to put 1 last and n first. So n plus n minus 1 plus n minus 2 plus ... plus 2 plus 1. And the reason I'm doing this is because if we look at the numbers that are on top of each other, 1 plus n, and then 2 plus n minus 1, what's that? 3 plus n minus 2, what's that? 4 plus n minus 3, what's that? All of these are n plus 1. I have n plus 1 plus n plus 1 plus n plus 1 plus etc. How many of these do I have? Well, we can count them. 1, 2, 3, all of the way up to n. I have n lots of n plus 1. So n multiplied by n plus 1. 2 times the number that I want is equal to n plus 1. Divide both sides by 2 and we get our formula. The sum of the first n natural numbers is n multiplied by n plus 1 over 2. We're going to need this later. 2 more formulae which we're going to need. These can be proved in perhaps similar ways, but it's more difficult, so I'm not going to prove these. The sum of the first square numbers is n plus 1, 2n plus 1 over 6. And the sum of the first n cubic numbers is n plus 1 over 2, all squared. I will remind you of these formulae when the time comes to use them. Now, let's go back to this area that we were talking about before. R is the region underneath the graph of y is equal to 1 minus x squared, above the x-axis and to the right of the y-axis. And I want to calculate the real area of R. We've done some approximations. We know roughly what it is, but I want to calculate its exact area. And I'm going to use a lower sum to calculate its area. First, I'm going to write down a formula for the lower sum with n rectangles, and then I'm going to take the limit as n tends to infinity. So here's what we're going to do. We're going to take our interval, our closed interval from 0 to 1, and we're going to cut it into n pieces which all have the same width. They're all going to have this width 1 divided by n. So here we go. So we're going to have a first subinterval from 0 to 1 over n. And then our second subinterval is going to go from 1 over n to 2 over n, and then from 2 over n to 3 over n, etc. And on each one of these little pieces, on each one of these little subintervals, we're going to draw a rectangle so that the rectangle fits inside R. And the way we do that is we use the right-hand side of the rectangle to decide its height. If our function is decreasing, we would use the right-hand side. If our function was increasing, we would need to use the left-hand side instead. So only right-hand side for a decreasing function. So for example, this is very small, but hopefully you can see it. This is the point 1 over n, f of 1 over n. and this is the point 2 over n f of 2 over n. And then step 3, after we've got our formula, we're going to take the limit as n tends to infinity. So what are the areas of these rectangles? Well, the first rectangle has width 1 over n, and its height was decided by the right-hand side, so the height was f of 1 over n. Second rectangle has the same width. All these rectangles have the same width. The width is always 1 over n. The height of the second rectangle is f of 2 over n, so the area of the second rectangle is 1 over n, f of 2 over n, and so on. I've tried to draw the kth rectangle just here. The kth rectangle has width 1 over n and height f of k over n. So area 1 over n, f of k over n. We want to add these all together. The area of these n rectangles, add them all together, we get a sum from k is equal to 1 to n because there's n rectangles. The width of the kth rectangle is 1 over n, the height of the kth rectangle is f of k over n. We're going to play with this and we'll end up with a nice formula at the bottom. So our function is 1 minus x squared. So we have the sum of 1 over n, and then instead of f of k over n, we have 1 minus k over n squared. Or if we want to, we can write that as the sum of 1 over n minus k squared over n cubed. We can split that into two sums. Why n cubed? Because there's an n just here, there's an n just here, and the second one is squared. 2 plus 1 is 3. And then we want to simplify this. The first one is easy. The first one is just 1 over n plus 1 over n plus 1 over n plus 1 over n, etc. N lots of 1 over n. For the second sum, k is changing as we go through the sum, but n is a constant, so the 1 over n can be taken outside. I get to n times 1 over n minus 1 over n cubed, and then sum of the first n square numbers. But we know that. I've given the formula for that earlier. The sum of the first n square numbers is just n plus 1, 2n plus 1 over 6. So I want to take that and put that in here. 1 minus 1 over n cubed multiplied by n plus 1, 2n plus 1 over 6. Or cancel out the n's, we get 1 minus 2n squared plus 3n plus 1 divided by 6n squared. I'm cancelling one of the n's on the top with one of the n's on the bottom, so we could just get n squared on the bottom. This is the formula for the area of n rectangles in a lower sum. We want to take the limit as n tends to infinity, and then we will find the true area of R. And you know how to do limits as n tends to infinity of a rational function like this. Divide the top and the bottom by the biggest power of n, so divide by everything by n squared. We get 2 plus 3 divided by n plus 1 divided by n squared on the top, and on the bottom we just get 6. Take the limit, we get 1 minus 2 over 6, or 2/3. This tells us that the area of the region R is 2/3. And that's what we were guessing when we were doing the lower sum, midpoint sum, upper sum for many, many rectangles. When we looked at it, the table which had 1,000 rectangles, we saw that we were getting close to 2/3. Let's make this a little bit more general. Let's suppose we have any function, any continuous function, defined on a closed interval from A to B. What I want to do is I want to take the domain of this function, the closed interval from A to B, and I want to cut it into n little pieces, n subintervals. But we're trying to be as general as possible. So this time, the pieces don't have to all be the same size. We could have some small pieces and some big pieces. That's okay. Inside each one of these little subintervals, we're going to pick a point and call it CK. And this will be where we decide on the height of each rectangle. And for the width of each one of these little subintervals, we're going to call that capital delta xk. So for example, delta x1, the width for the first interval, well, the first interval goes between x0 and x1. So that's going to be x1 minus x0. On each one of these little pieces, on each one of these little subintervals, we're going to draw a rectangle which has width, capital delta xk, and has height f of ck. So we're going to have a picture that looks something like this. For the kth rectangle, we have a rectangle of width, delta xk, and height f of ck. Now, wait a minute. If f is negative, if f of ck is negative, then the rectangle we draw is going to go downwards. So it's going to have, inverted commas, negative area. That's okay. That's what we want. When the function is positive, we want to have positive area. When the function is negative, we want to have negative area. And then we can add these areas together. We get the total area of n rectangles. The sum from k is equal to 1 to n of the height multiplied by the width, f of ck multiplied by delta xk. This is called a Riemann sum for f on the interval from A to B. And then we want to take the limit as n tends to infinity of this Riemann sum. But let me be more precise here. It's not okay if we have lots and lots of tiny intervals, which are getting smaller and smaller, and then we have one big interval. We don't want this. When we increase n, we want all of these little pieces to decrease. We want the width of all of the rectangles to decrease. So actually, we don't want the limit as n tends to infinity. We need to be a little bit more careful. Actually, we want the maximum width of the rectangles to tend to 0. So if you want to, you can think of this as n tends to infinity, and in practice that's what we're going to use. But really what we need is that the maximum width of the rectangles tends to 0. Sometimes this limit exists, and sometimes this limit does not exist. And that brings me to the halfway point of what is going to be a short lesson this week. So let me ask you a question. Should we take a break to say 3 o'clock and then carry on, or would you like me to continue? Okay, so 6 people have voted and everybody says no break, continue. So let's continue then. We'll be able to finish in another 30 or 40 minutes. Our final topic for this week's lecture is the definite integral. And we're interested in the limits of these Riemann sums. We can write down a Riemann sum for a function f on a closed interval from a to b, and then we can try to take the limit as n tends to infinity. And as I just said, really, we're not really taking the limit as n tends to infinity. Really, we're taking the limit as the maximum width for these rectangles tends to 0. If this limit exists, then it's called the definite integral of f over the closed interval from a to b, and we write it like this. This stretched letter s, and then an a at the bottom, a b at the top, a function f of x, and then dx, if the limit exists. Before I go on, we need this limit to exist and to be the same for any Riemann sum that we could write down. Remember, when we're creating a Riemann sum, we choose how to split our interval up into little pieces, and we choose where we're going to measure the height of the rectangles. We're choosing these numbers 6k inside, ck inside each interval, but we can choose where we put them. We might put them on the left, on the right, in the middle, a little bit to the left of the middle. It's completely up to us. We need the limit to exist, and we always need that the limit is the same, no matter where we choose ck and no matter which little intervals we choose. Your textbook describes this a little bit more, I would say a little bit more complicated way, because your textbook defines definite integral in terms of epsilon and delta. Let's just go through that briefly. Let f be a function defined on a closed interval from a to b, and we say that a number j is the definite integral of f over ab, and that j is the limit of the Riemann sums if the following is conditioned. And then the second part of this is just about limits. This is doing the epsilon delta definition of the limit. So it says, for all epsilon greater than 0, there exists a delta greater than 0 such that, and it says for every partition, so if you remember, I took my interval from a to b, and I chopped it up into lots of little pieces. Some were big, maybe, some were small, chopped it up. That's the idea of doing a partition. The definition says, any way you want to chop our interval up, so any partition, if the maximum width of each one of these pieces, whichever one is the biggest one, is smaller than delta, and if we can choose, if we take any choice of ck inside each little piece where we measure the height, we need to have that the Riemann sum is very, very close to the number j. So this definition is effectively the same as what I did on the previous slide, but this is in terms of epsilon and delta. The notation looks like this. We read this as the integral of f from a to b. This stretched letter s is an integral sign. Why is it s? Because we're doing sums. We're doing Riemann sums, and then we're taking the limit of the Riemann sums. Sums start with the letter S. So an integral sign is a stretched letter S. The A on the bottom of the integral sign is called the lower limit of integration. The B on the top is called the upper limit of integration. The function that we're integrating is called the integrand. And the dx on the end tells us that x is the variable of integration. And what does it mean? Well, as long as we have a positive function, the integral is equal to the area between the function and the x-axis between a and b. If we have a negative function, we have this idea of negative area. Area underneath the x-axis we think of as a negative area. If the definite integral of f from a to b exists, then we say that f is integrable on the closed interval from a to b. So just as if a derivative exists, we say that the function is differentiable. If the definite integral exists, we say that f is integrable. For example, the function we've just looked at in the previous section, 1 minus x squared, this is integrable on the closed interval from 0 to 1, and the value of its integral is 2/3. We actually didn't completely prove this because we only did lower sums. If we were going to prove this completely, we'd have to prove that it didn't matter which type of Riemann sum we did. When we take the limit, we always get 2/3. So some details I've skipped there. And let me just remark that it doesn't matter which letter we use. The integral of from a to b of f of x dx is the same as the integral from a to b of f of u du, and that's the same as the integral from a to b of f of t dt. The variables in red are called dummy variables because it doesn't matter which letter we use here. Theorem: if f is continuous on a closed interval, then f is integrable on that closed interval. Anytime we have a continuous function, then straight away we know it's integral. We don't need to do any extra work. We don't need to test to see if all the Riemann sums have the same limit. If the function is continuous, then it must be integral. And we can actually generalize this a little bit. Look at this picture on the right. If we have the type of discontinuity which jumps from a finite number to a different finite number, this is called a jump discontinuity. So that's not the type of discontinuity which goes up to infinity. It's always jumping from a finite number to a finite number. If f has finitely many jump discontinuities, but is otherwise continuous on the closed interval from a to b, then f is integral on the closed interval from a to b. Now I want to give an example of a function which is not integral. I'm going to define g on the closed interval from 0 to 1 by the formula g of x is equal to 1 if x is a rational number, g of x is equal to 0 if x is an irrational number. And I'm saying that this function is not integrable on this interval. And I want to explain why. Remember, when we set up a Riemann sum, we choose the point CK where we calculate the height of each rectangle. If we always choose a CK in the rational numbers, then we're always going to have g of ck is equal to 1. So then when we set up the Riemann sum, we're always going to have 1 multiplied by the width of the rectangle. And if you add all these widths together, of course, we get the width of the interval that we started with, which is 1. But if we choose an irrational ck, if we choose ck which is in the real numbers but not in the rational numbers, then we would always have that g of ck is 0. Then when we write down the Riemann sum, the height of the rectangle would be 0 and the width of the rectangle would be delta xk. And of course, 0 plus 0 plus 0 plus 0 plus etc. is just equal to 0. So for at least one Riemann sum, the Riemann sum is always equal to 1, and for at least one Riemann sum, the Riemann sum is always equal to 0. Take the limits of these and we don't get the same number. The limit of 1 is not the same as the limit of 0. That means not every Riemann sum has the same limit. There does not exist a common limit of the Riemann sums, so therefore the function is not integrable. So to summarize, if we have a nice continuous function, we know that the function is integrable. If we have something weird like this, then it's possible that the function is not integrable. I want to go through some properties of definite integrals. In this theorem, we're going to suppose that f and g are integrable functions, and we're going to suppose that k is a number. Rule number 1, which is more of a definition than a theorem really, but I'm writing it in a theorem. The integral from a to b f of x dx is equal to minus the integral from a to b f of x dx. What that means is you can swap the upper limit of integration and the lower limit of integration. We can swap their places around as long as we put a minus sign in front of the integral. We'll be using that later today. Rule number 2 is like a constant multiple rule for definite integrals. If you have a number k inside an integral, you can always take it outside. We know that's true for limits. We know that that's true for derivatives. We know that's true for indefinite integrals. And now this theorem says this is also true for definite integrals. Rule number 3. An integral from a to c, so that's this blue bit, plus an integral from c to b, that's this pink bit, is equal to the integral from a to b, which is all of it. Well, we can see that from the picture. All of this area, which I'm colouring in green, is equal to the blue area plus the pink area. Rule number 4. The integral from a to a of a function is equal to 0. Look at the picture. What is the area of this little blue line? This blue line has width 0, so its area must be 0. Rule number 5 is the sum rule for integrals. Integral of a function plus a function, we can split this up into 2 integrals. Integral of f plus integral of g. We've had a sum rule for limits, a sum rule for derivatives, sum rule for indefinite integrals. Now we also know that the sum rule is also true for definite integrals. Rule number 6, property number 6. First, forget about the right-hand side. Let's just talk about this left-hand inequality. Look at this green rectangle just here. This one. The width of this rectangle is b minus a, and the height of the rectangle is chosen so that it's less than the function. Height is equal to the minimum of f. So this thing I have over here on the left, b minus a minimum of f, is the area of this green rectangle. And this part of the theorem says the area of the green rectangle is smaller than the area of this blue region. That's all of this. Let me draw that again. All of this. Well, we can see that from the picture. We can see that the green area is smaller than the blue area. We can also see that the blue area is smaller than this orange rectangle, all of this. And the area of the orange rectangle is width b minus a multiplied by height maximum of f. Area of the blue region is smaller than the area of the orange rectangle. Yeah, we can see that from the picture. Property number 7. If G is always bigger than F between A and B, we only need this to be true between A and B. It doesn't matter what happens over on the left. It doesn't matter what happens on the right. We don't care. We only care what happens between A and B. And between A and B, we want that F is smaller than G. If that's true, then the integral of F is smaller than the integral of G. That makes sense. We can see from the picture that this blue area is going to be smaller than the pink area. And almost the same thing, but by setting one of the functions equal to 0. If G is greater than or equal to 0 between A and B, then the integral of G over A from A to B must also be positive. Property 9 is about even functions. Let me remind you, an even function is a function where the left part of the graph is a mirror image of the right part. And this rule says the integral from minus a to a, so that's everything here, is equal to 2 times the integral from 0 to a, which is the pink part. And yeah, we can see that from the picture. All of this area is 2 times the pink area. Rule 10, the final rule, is about odd functions. If f is an odd function is a function where we can take the graph and we can rotate it by 180 degrees, and we have exactly the same graph. If f is an odd function, then the integral from minus a to a of f of x dx is equal to 0. Well, look, we have a positive area here, and we have a negative here. Positive plus negative is 0. I also have a positive bit over here and a negative bit just here. Positive plus negative is equal to 0. The integral of an odd function, if it's between minus a and a, is always equal to 0. Let's do an example which uses these rules. We are told that the integral of f between minus 1 and 1 is 5. The integral of f between 1 and 4 is minus 2. And the integral of h between minus 1 and 1 is 7. Then we can calculate the integral from 4 to 1 of f. Rule number 1 was we can swap the upper limit and the lower limit around as long as we put a minus sign in the front. So we get minus the integral from 1 to 4, f of x dx, And the question tells us that, so it's minus minus 2 or plus 2. We can do the integral from minus 1 to 1 of 2f plus 3h. So what do we know? We know the integral from minus 1 to 1 of f, and we know the integral from minus 1 to 1 of h. We want 2 times the first integral plus 3 times the second integral. 2 times 5 plus 3 times 7. And we can do the integral from minus 1 to 4. We know the integral from minus 1 to 1, and we know the integral from 1 to 4. Using one of the rules, I forget which one, integral from minus 1 to 4 is the same as integral from minus 1 to 1 plus integral from 1 to 4. So 5 plus minus 2. For example, show that the integral from 0 to 1 of the square root of 1 plus cos x dx is less than or equal to the square root of 2. Well, we had one of the rules about this. Let's look at the integrand first. The integral, sorry, the square root of 1 plus cos x if x is between 0 and 1. What is the biggest that this could possibly be? What is the biggest possible value of cos x? The biggest possible value of cos x is 1. So the biggest possible value of the square root of 1 plus cos x is square root of 2. Therefore, our integral must be less than the width of our interval, 1 minus 0, multiplied by the maximum of the integrand, or 1 multiplied by root 2. And that's it. That's the answer to this question. Calculate the integral from minus 2 to 2, x cubed plus x dx. Our integrand is an odd function, and we're integrating from minus 2 to 2. So we're symmetric about the y-axis. We have from minus a to a, here from minus 2 to 2. Straight away, we can write down that the integral of an odd function from minus 2 to 2 is always equal to 0. Calculate the integral from minus 1 to 1 of 1 minus x squared dx. X squared is an even function because 2 is an even number. 1 is an even function. So 1 minus x squared is an even function. The rule for an even function is that the integral from minus 1 to 1 is equal to 2 times the integral from 0 to 1, because the left side of the graph is the same as the right side of the graph. And we know this integral is equal to 2/3. So we just multiply 2/3 by 2 to get 4/3. Calculate the integral from 0 to b of x dx for b greater than 0. I'm going to solve this question 2 ways. In my first solution, I'm going to use a Riemann sum. The function is continuous. That means the function is integral. That means all of the Riemann sums have the same limit. So we only need to write down one Riemann sum and then take its limit, and we will find the same limit that all Riemann sums have. So let's make this as easy as possible. Let's cut this into n pieces which all have the same width. So I'm going to be doing my cuts at b over n, at 2b over n, at 3b over n, etc. And I'm going to choose ck on the right-hand side of each one of these little sub-intervals. Why? Just because it makes the calculation easy. the width of all of these little intervals is always going to be b over n. They all have the same width. So the idea is we're doing this. We're going to do an upper sum. We have an increasing function, and we're choosing the right-hand side of each little sub-interval to decide the height of the rectangle, and that's going to give us an upper sum like this. It's an upper sum because the area of these rectangles is going to be bigger than the true area. So this is how we do our Riemann sum. The sum from k is equal to 1 to n, because we have n rectangles. Height of the rectangle multiplied by the width of the rectangle. The height of the rectangle is kb over n, because our function is just f of x is equal to x. And the width of each rectangle is b over n. B is a constant, n is a constant at the moment. So that's just b squared over n squared multiplied by the sum of k. And we did that one. That was the one where I did 1 plus 2 plus 3 up to n, and then I did another row plus n minus 1 plus n minus 2, etc. Earlier today, we found that that is n plus 1 over 2. So the sum of n rectangles in an upper sum is b squared over 2 multiplied by 1 plus 1 over n. And what do we get if we take the limit as n tends to infinity? Of course, the limit of 1 over n is just 0. So we just get b squared over 2. So the answer to this question is the integral from 0 to b of x is b squared over 2. Now let's solve this question a different way. We want to calculate the area of this pink region, but this pink region is just a triangle. And we know how to calculate the area of a triangle. It's just a half multiplied by base multiplied by height. So half multiplied by b multiplied by b. So this time it was easier this way. B squared over 2. That shows that our limit of Riemann sums is working. The limit of the Riemann sums is really giving us the area of this triangle. Now that we have this, we can calculate, or we can write down, the integral from a to b of x dx. Because remember, the integral from a to 0 plus the integral from 0 to b, if we're adding two integrals of the same function together, and if the upper limit of one function is the same as the lower limit of the other function, we just get the integral from a to b. And this one on the right, we know that this is a half b squared. What is the integral from a to 0x dx? Well, we can just swap the a and the 0 as long as we put a minus sign in the front. So that's minus a squared over 2 plus b squared over 2. Or writing it another way, that's b squared over 2 minus a squared over 2. And that's all I want to say this week. Next week, we do not have a lecture. Our next lecture is in 2 weeks' time. And in 2 weeks' time, we're going to start properly doing integration. We're going to start with the most important theorem in this course, the fundamental theorem of calculus. In mathematics, anytime a theorem is called a fundamental theorem, then immediately you know this is an important one. And that's true for this course as well. The most important theorem in this course is the fundamental theorem of calculus. We'll start with that in 2 weeks' time. And then we'll do indefinite integrals and the substitution method, and then substitution and area between curves. Are there any questions? Yes, second exam is on the 25th of April.